4. We talked about something called a definite integral. It looks like this. And we know this represents what? Represents the area under this function from one point to another. And we evaluate it by finding the antiderivative of f. We find this function, capital F, is the antiderivative, and we evaluate it on 2 endpoints and find the difference. Well, we also have a notation here like this. It's handy to have a way to refer to this function. And this might be confusing, and maybe it'll feel really natural, but the notation we use is just this. I'm sorry. That is, instead of giving endpoints to the integral, to the definite integral, we just leave them off. And we have what we call the indefinite integral. The point I've been making up till now is a definite integral here. This is a number. The indefinite integral is a function, or generally it's a family of functions. Remember, we're always going to have attached here some variable constant. So it's a bunch of functions that you can move up and down by adjusting this. Some problems you'll see there's actually information. So, okay, here's a simple example. If I said indefinite integral of x, well, we know the antiderivative is just x squared over 2 plus some constant. We already have a whole list of antiderivatives we know, so we can enumerate them. I guess at the risk of repeating myself from Tuesday, we have these inverse power law function formula. That's for n not equal to minus 1. We have x equal minus 1, which is just 1 over x. We know that's log of the absolute value of x. That's the one fly in the ointment when you're going backwards. There are all these real obvious ones. E to the x is, of course, going to just be e to the x. You can differentiate it or minus antiderivative all you like. You always end up with e to the x. Although when you're going in the integration direction, you tag on these constants that you have to worry about. Sine of x, of course, is negative cosine of x. Cosine of x and sine, and so forth. You just think of a formula over here for a derivative, and you get its antiderivative. And so you have things like over x squared plus 1, which become the inverse tangent of x. All those little formulas come in handy. Even though it's a different kind of object, it's not a number, the indefinite integral inherits all the same nice properties of a definite integral. You have some constant times a function. That constant can go outside the integral sign. That is, the antiderivative of a constant times a function is just a constant times the antiderivative of the function. Constants just move in and out nicely. The sum of two functions, the integral of the sum of two functions, can be separated. So if you have some complicated mess like this, you don't have to sweat it because you can do each piece separately, right? You've got e to the x on the value of x minus and the same strategies that you can use to find antiderivative when you're doing a definite integral, you can apply. You can apply to indefinite integrals. I showed you this on Tuesday. You have the derivative of a function over a function. You're trying to find the integral. That's just the log of the function, the absolute value of the log of the function. I know I did this example today, but I think it's worth repeating here. I have 2x plus 1 over x squared plus x plus 4. I happen to notice the relationship between these two. If f of x is x squared plus x plus 2, its derivative, very conveniently, is 2x plus 1, fitting my pattern. So I know that this becomes the log of the absolute value of x squared plus x plus 2 plus a constant. All right. So just like with definite integrals, we have a whole toolkit. Fixed things. We have some rules we can use, and we have some formulas and some patterns we can look for. I guess kind of to complete the circle, I want to say that I have some indefinite integral. I can use this to solve the definite integral. I have AB f of x. This may seem a little obvious, but this is the indefinite integral of f of x dx, which itself is a function or a family of functions, and I can evaluate it at the endpoints. This is kind of completing the circle on the fundamental theorem we looked at. So, I guess with that in mind, I hope you have some paper handy. I'd like you to try a few examples. Let's start with well, let's just start with this. Square root of x dx. It's the anti-integral, the indefinite integral of this antiderivative. Is Genome hiding there behind something? Oh, okay. Catch up. So Calvin is not here. Meryl is not here, and Emily. You're Emily? Oh, you're Will. Okay. Oh, I'm sorry. Thank you for letting me know. Earl, you took the exam, right? You're, oh. Okay, all right, I got it. I caught up. All right, anyone? Square root of x. This is a pretty simple one.
Two x to the power of 3, 2x to the power of 3 over 2, and then divide the whole thing by 3.
Okay. Anyone have a question how she found that? You have a formula? I want to emphasize that when you're trying to figure these out, sometimes the process to find the antiderivative or, you know, indefinite integral itself, oh, we left off something, by the way. Right. The process to check it is often much easier because finding the derivative is straightforward. If I have 2/3 x to the 3/2, I know for my power rule, the derivative of that is just 3/2 times 2/3 times x to the 3/2 minus 1. These cancel and we just get x to the 1/2, so that's our check. Let's try something a little more challenging. Cosine of x over sine x to the 5th. Conveniently erase the formula, but that's okay. All right, anybody have some thoughts on this? Any suggested answers? Had an interaction at the bus stop today. Got off the bus and was waiting with an adult and his very young, precocious child. He was having her read the sign. She was just in think in nursery school or kindergarten, she was learning the alphabet. So read the sign. And tried to get her to read the sign. I said, she knows numbers too. So we talked about it, and he says, well, what do you need algebra for? I said, well, not everybody does need algebra. This notion that everyone in high school now has to pass algebra as if they're going to use it. But there are a lot of things you need algebra for. You need, just as a basis, if you're going to go into any kind of science, business. Got me thinking, kind of draw a graph. So, kind of goes like this. This time. Kind of go like that, I think. This is 0. This is the end of the semester when your finals are over. And I think this is like interest. So you show up and all of a sudden, it's really, oh, I've got to get on top of this. And it kind of wanes, and then this is kind of the week before finals. All of a sudden, interest is really high. It's almost as if there's a biological process involved. You know, like bacteria. They kind of get exponential growth for a while. So they start running out of food, and then, well, I'm not comparing, it's a different graph. I'm not comparing students with bacteria. I'm sorry, I lose my job over that. All right, anyone have anything here? No? Yes?
Negative 1/4 times 1 over sine of x to the 4th plus c.
To the 4x plus c. Okay. Well, if you're not clear on how to get there, if you notice cosine is the derivative of sine. You could use that formula, or you could kind of power your way through it. You could kind of go, well, x to the negative 5th, you have to start with sine of x to the negative 4th. I find the derivative of this is going to be sine of x to the negative 5th, negative 4 times it, times cosine, the chain rule. So really all I have to do is compensate for that minus 1/4. You also can test your results quite nicely. I write this as negative 1/4 sine to the negative 4 of x. And I find the derivative using the power rule and the chain rule. Negative 4 times negative 1/4 is just 1. So I just get sine to the negative 5th. Again, times cosine of x. That's what I'm looking for. All these are good. Let's, in 2 steps, let's kind of up the ante a little. I'm going to draw the graph of this in a second. From negative 1 to 3 of x plus 1. Now we're going to have to find an indefinite interval and then compute it. why don't you start with that? So we get, this. You don't have a number yet? How about an antiderivative? Does anyone have an antiderivative yet? Maybe it's not interest, maybe it's like energy. Zero. Anyone? Yes?
X cubed over 3 minus x.
Okay. And, have you computed that yet?
Yeah, it was 16 over 3.
16 over 3? Okay, so let's look at that. Here's your graph. -1 to 3. And we have here some negative area, some positive area. So if this were traveling, this would tell us, well, we went backwards and then forwards, and this is how far we went. But if instead of knowing where we are, we wanted to know the distance traveled, I might want to do this, and I would get a different answer. So how would we do that? How do we figure that out? Any ideas? Talked about this. So you won't always have a graph to look at unless you like to plug it in your calculator. the function goes through 0 here. The area changes direction. Since it's below, here it's below the axis, here it's above the axis. So we want to know where that point is. We want to know where x plus 1 times x minus 1 becomes 0. Well, assume everyone here can just blink and go, well, at minus 1 and 1. Well, minus 1 is over here where we're starting, so that's not important. So let's just hit 1. So we use this feature of a definite integral. It tells us to integrate from 0 to 1. Find the absolute value and add it. Well, when you're doing this kind of problem, it's nice to know that Isabella, having already informed us, we don't have to repeat, because it might end in this x. Not really doing anything here. And then you just have to compute these. Or, for a simple problem, you can probably get away with just doing it on your calculator. Yes?
Why would it be -1 to 0 instead of -1 to 1?
Ah! That's because you're the only one paying attention to the teacher's mistakes. Yes, thank you. There we go. Much better now, right? All right, it's a nice exercise. There's a few more things I want to cover here, having to do with integration, integrals, whatnot. This is just a you ought to know kind of thing. So, if faced with this ominous looking integral, what can we do with that? This is definitely not the derivative of this, so that log function thing is not going to help us. But I wonder if you do the quotient rule backwards. Dividing something by t, so it ends up, no. This is actually very easy. You just look at this and you go, well, wait a minute, I can simplify this. T to the 5th over t squared, that's just t cubed. T cubed over t squared is just t. Squared over t squared is 1. Minus 8t over t squared is minus 8 over t. And plus 5 over t squared. Well, everything here is within our grasp. This is going to be t to the fourth over 4. It's going to be t squared over 2, so just 2t squared. All right, dx dt. T problem. 1, well, that's just t. Minus 8 over t, that's the log of t. 5, okay, that's going to be over t times minus 1. So, you know, just simplify and break it up, and straightforward. All right, I have a problem I want everyone to try. Good question?
Yeah, for the negative 8 over t, doesn't the 8 have to be in there somewhere? It's not just log of t.
Oh,
Is it? Yeah.
thank you. Thank you. Yeah, that's the students, as a teacher here, he's like all excited. I didn't lose that much energy, but I'm focused. Having a little focus issues. Okay, so this might be a hard problem. If you see it, it's not hard at all. And it has a kind of a moral that I want to get to. I want to find that antiderivative. Talked about how to do it. You just have to see connection. So they either want to see answers popping out or I want to see steam coming out of ears. When you think you have it, or you've gotten somewhere but you're at a stopping point, just take your pencil and hold it vertically so I can see and take a hold here. Two, 3, 4, 5. Okay. What do you say at the end of the, let's take these pencils down. Okay, so to do this, you need kind of need a little pattern matching. First thing you want to think of is, well, let's call something f of x e to the x, right? Doesn't it scream for that? And for that matter, prime of x is also e to the x. If I look at this, and what is it? It's kind of f of x e to the 2x, that's e to the x squared. So that's f of x squared. Then, thinking, what's going to be useful here? You go, well, might as well call that f prime of x. Because that looks an awful lot like this. Which we should all know what that is. Right? That's the inverse sine of x plus c. So that suggests that the solution to this is inverse sine of f of x. Let's go backwards. Oh, which of course is e to the x. Well, if we're not sure, we say, all right, what is the derivative sine of e to the x? Composite function, I'm going to use a chain rule. Derivative of inverse. Derivative of the inverse sine, 1 over square root of 1 minus, e to the x squared, that's e to the 2x, times the derivative of e to the x, that's e to the x. That's what I wanted. So again, evaluating these, a lot of it is kind of, first you got to work backwards, then you can work forwards to check. Maybe you have to adjust. Maybe there's a constant you missed. So, look at this whole process and think, this is kind of a general problem here. Find the derivative of some composite function. That's derivative at that function times the derivative of the internal function. It's kind of a more general problem. It could seem that the key to this is when you're trying to go backwards is to look at this and identify these functions. We can identify these functions, we can work backwards to where we want to go. We're going to look at this on Tuesday in more depth. This is going to be called substitution. And again, the strategy is to see, typically to find out what g prime of x is. So let's look at an example, just one quick example to give you a feel for this. Okay. So we look at this and we say, oh, well, this is kind of f of g of x. We think of g of x as 2x plus 1. And f of x is square root of x, right? Well, our g prime here would be 2. rather nice. That's just a constant. Those are easy to deal with. So, well, I'm not going to go into the process. We're going to go into the process on Tuesday. That's going to be the end of our search for ways, interesting ways to do antiderivatives in this class. And we're going to do some applications of reducing volume. I think there's another subject in there. For those of you who are going to go on to Calc 2, you're going to spend some time learning other ways to find antiderivatives akin to this. And I just wanted to, for those of you who are going to miss out, again, this isn't part of the curriculum, but I just wanted to give you a feel for where this stuff goes. The first place it comes from is, look at for a second here. What if you have the product of two functions? All right, the derivative of two functions, that's f of x, u prime of x, plus g of x, f prime of x. Well, we wanted to find this integral. Or rather, let me restate that. If we wanted to find the integral of two functions, make something x log of x. This might help us. How? Well, if I take the integral of both sides, over here I'm just going to get f of x plus g of x. Here I'm going to get the integral f of x g prime of x plus integral of f prime of x g prime of x. And I can rewrite this. I can solve for, say, this. F of x, g prime of x, dx equals f of x plus f of x plus times, where did the plus come from? Plus f of x, g of x minus integral f prime of x, g prime of x. So the idea is I have something here and it looks ugly. I have the product of two things. I can kind of switch their relationship here. If I find the antiderivative of g of x and the derivative of f of x, right, I can find that. If that integral is easier to do than this one, then I just use this formula. So how would that work? I'd look at this and I'd say, well, maybe f of x is x, g of x equals x, and f of x equals log of x. So this tells me by my formula that this is, well, g prime of x is 1, f prime of x is 1 over x. So it says that the derivative of, I guess I have to make g of x. I knew I did it wrong. Let me try again. I want this to be f of x g prime of x. So let's make that x as x over x squared over 2. All right. So now, integral of f of x log of x times x becomes g of x times f of x, which is x squared log of x minus f prime 1 over x times g of x, x squared over 2. Well, this integral is easy. So that's another strategy. We're not gonna, of course, we're not gonna cover it. And there's just one more technique I'm gonna throw by you. What happens if you have something like this? Well, trick here is, can we break this up somehow? All right, we look at x squared minus 3x minus 4, that's x minus 4 times x plus 1. So we have x minus 4 times x plus 1. And we want to break that up into something that looks like this. We can do that. We can solve for a and b. Now we have an integral we can do real easily. Right, it's just the log of x minus 4 plus times some constant plus the log of x plus 1. So that's another strategy that you might run into. All right. I think that's all I have for today. As I said, we're going to look at substitution on Tuesday. Substitution will be the last subject that will be seriously on the exam. The other subjects, maybe, but not like